Well, hopefully you were able to attempt this on your own. As I go through it here, I realize I kind of should always have a line for the 0 time second, like the instant before you begin this. So I inserted that. So don't mind me. At time 0, they haven't stepped out yet. We know that objects on Earth accelerate at a rate of 9.8 meters per second per second. So I guess I'll be real precise here. After 1 second goes by, they should have picked up enough speed to be 9.8 meters per second, okay? After 2 seconds, it's going to continue to, it's constantly accelerating at this rate, right? So it's going to pick up that speed again and kind of add it to. So 9.8 plus 9.8 gives us a speed. After 2 seconds, then he's going 19.6 meters per second. And you can kind of see the trend. We'd add another 9.8. For 3 seconds, he's going almost 30 meters per second. It's getting kind of scary. 4 seconds, we're looking at 39.2 meters per second. And after 5 seconds, 49 meters per second. So this is an object that's continuously accelerating at that rate g, 9.8 meters per second per second. Now, in real life, does this happen? No, because we have a force that acts against that constant acceleration. That's air resistance. So realistically, after 5 seconds, would he be going exactly 49? No, but it's nice in physics to illustrate how these numbers actually work by assuming that we don't have to worry about things like air resistance. So in a question like this, I'll make sure to insert that, like, hey, assume air resistance doesn't matter or friction doesn't matter, stuff like that. Projectile motion is really interesting. A projectile is something, it's a falling object with forward velocity, we say. So as we shoot a cannonball, yes, it's falling. Yes, it's shot forward. And I want you to notice the arc that it typically makes. Anything can be a projectile: an arrow, a dart, a baseball, a spitball. Even my baby Isla's a projectile when I toss her up in the air a little bit and catch her. I don't like to do that, but my husband does it more than I do. So it's anything thrown, shot, batted, not under your own power. That means it doesn't have like a little motor that's propelling it. Those drones are not projectiles because they are under their own power. The motion of a projectile has two components, a horizontal and a vertical component. It says the horizontal motion is produced by things like your arm, your bat, the bow. It's parallel to the Earth's surface. That's what horizontal means here. And the horizontal velocity we assume is constant when we ignore air resistance. That speed you initially, let go of the ball with is going to be constant when we don't have to worry about things like air resistance. That's why in this picture we see every second that passes, the same distance is traveled. On the other hand, though, that vertical motion is kind of interesting. It's caused by gravity. It's perpendicular to the surface. And you see that as time passes, the space increases. And that's because falling objects accelerate towards the ground. That's because of gravity. And so you'll see that it goes farther and farther every second that passes. The vertical and the horizontal motion is independent of one another. A ball shot horizontally, as the yellow one here, compared to one dropped from the same height, is going to both hit the ground at the same time. And that's because, although this one does have some forward velocity, it has nothing to do with how gravity impacts it. Gravity acts on these two balls the exact same way. And so they're going to land at the same time. This is kind of weird. A couple examples that, I guess I have a link here if you could access this in the notes. It's really a cool episode where the Mythbusters are testing, okay, you're telling me that if I shot a bullet horizontally from a gun and dropped a physical bullet from my hand from the same height at the same time, that they would land at the same time? That doesn't make sense, right? They put it to the test because most people think that bullet that you shoot, gosh, it goes so far down the line compared to the bullet that you just drop from the same height. You'd think that that one shot would land much, much later. But in fact, vertically speaking, they land on the ground at the exact same time. And they put it to the test, and it's really, really cool. So in projectile motion, vertical, horizontal motion, totally independent. I'm trying to think of other scenarios here, I guess. I guess I should say, however, that you can't tilt the gun so you're like shooting it upward. It has to be an exact horizontal shot. Just like in this picture here, it's a flat line motion. It's not like an arc, like you're shooting a basketball, because that obviously would impact when it would land. But these two objects landing at the same time, pretty cool. Physics is awesome. Let's talk about some specific forces. Friction is defined as a force that opposes motion of materials that touch. Friction isn't always a bad thing. In fact, it's really good. Like if we're wanting to walk on slippery ice, having those grippy shoes come in handy. It can be annoying, though, if it is causing your engine to run inefficiently. Static friction acts on objects that are not moving. Acts opposite to an applied force. And a good example is this guy trying to push this car. The car's not moving. He's trying to overcome static friction just by pushing against it. And hopefully, he might be able to do it. It looks like a Prius or something. Sliding friction opposes the direction of motion of a sliding object. Obviously. It's weaker or smaller than static friction of an object. So in other words, it's easier to overcome than trying to budge an object that wasn't already moving. An example is a sliding box down a ramp. Rolling friction, this is pretty easy. Force between rolling objects and a surface. It is much weaker, much smaller than static or sliding friction, 100 to 1,000 times less. That's why it's so much easier to use a rolly chair than to even push just a standard dining room chair around. So examples include a ball, a wheel, ball bearing, those rolly chairs. Fluid friction opposes motion of objects through fluids. Now, fluids doesn't just mean liquid, it also means gases. So boats don't need brakes. It uses its brake basically allows more surface area between the water and its mechanisms. So that just allows it to stop. Air resistance is also fluid friction. However, a lot of people forget that air is considered a fluid. So don't be thrown by that. If I use that terminology, if I use fluid friction, remember it's either gas or liquid. Some factors that influence friction is the type of surface. Obviously, rough versus smooth is going to impact how much friction you experience. The amount of force pressing on the surfaces together. Example, a sliding box on ice versus a sliding box on concrete. A sliding an empty box versus a full box. That full box is going to experience much more friction than an empty one. And obviously, whether or not we use different lubricants, that's going to change how much friction you have. Friction changes motion to heat. It makes things run inefficiently, okay? If you've got a lot of friction in belts and pulleys, you're going to realize that, seems like some heat is being generated here because your engine can overheat. But even just the simple example is rubbing your hands together real quick. If you do that right now, that motion becomes heat pretty quickly. Now I'm going to stop here. We are going to get into Newton's laws of motion pretty quickly, but let me just check something here. I want you to do packet questions 18 through 27 when you get a chance. Thanks.